Okay, we can do this. So, yesterday I discussed what happens to the surface of a 3D topological insulator, which is described by a Dirac cone, looks like this, when we add disorder and we make it very large. Let me put this in. Let's see if it works. And this is what we found. A Dirac cone plus disorder gives us a positive beta function, which we now all understand what that means. It means that the surface, as I make it larger and larger and larger, it has higher and higher conductance, and it flows into this symplectic metal. I call it symplectic metal because it's T squared equal to -1 is the symplectic class. But once you're here, all transport properties are just characterized by weak antilocalization. That means, in particular, that in a transport experiment, you cannot distinguish between a topological insulator surface or just some two-dimensional electron gas with spin-orbit coupling. So once you've done this, you have lost all signatures of topology in transport. So if you take a big chunk of a topological insulator and you're a transport person and you want to show that it's topological, you're screwed. So what do we do? Well, we just don't make it very large. And one nice thing to do is to make it into a nanowire like this. And nanowires are blue, as everyone knows. So I want to talk about the physics of these topological insulated nanowires, and particularly I'm going to focus on 3 different types of modes, which are a perfectly transmitted mode, a chiral mode, and a Majorana mode, and I'm going to explain to you how you get these things in these wires with a little bit of assistance from a magnetic field and a dash of superconductivity. Okay, so that's the plan. Since this is the last talk of a fantastic day, I'm not gonna throw at you too many equations today. I'm mainly gonna draw pictures like this. They will mainly be blue or red, but I'll try to explain the physics in a kind of intuitive way. Remember to ask questions when you have them. Let's start with the perfectly transmitted mode. I did mention it briefly yesterday, but let's see here how it comes about. And then we have to start with something which, to me, came as a surprise. Now you do this exercise, and in fact you will do this exercise if you work very hard in the hands-on session. You just take a 3-dimensional topological insulated nanowire and calculate the band structure of it. And if you look at the surface part, so if you just diagonalize this equation, you get a band structure that looks like this, and there's a gap. Now, why is this surprising? Well, because everyone, since you were a kid, has told you that topological insulators are characterized by a surface which is gapless. But actually, if you take a topological insulator and make it into a wire, you get a gap. And the reason has to do with the fact that this Dirac fermion that is on the surface here, its momentum is locked to the spin. This means that if the momentum points in this direction, the spin points in this direction or so. If it points in this direction, the spin follows. So if I now think about what happens as I move around this surface, well, as I move around the surface, the momentum goes in a circle. As the momentum goes in a circle, the spin goes in a circle. And when I come back to the same point after encircling the cylinder once. Since the spin rotated by 2 pi, the wave function comes to minus itself. Now, if you just solve this equation, Dirac fermion with anti-periodic boundary conditions, this is what you get. Now, these wires, when you make them, are relatively large. They can be a couple of 100 nanometers in width. So then you say, well, then this gap must be tiny, so I can forget about it. But that's actually not true. If you take, this is the gap, it's just a quantization gap, and now W is the circumference of the wire. If I take a circumference of 380 nanometer, this is a typical wire that they have in experiments, then I get a gap of 6 millieV, which, if you're a theorist, maybe it doesn't mean anything. But it's a large enough gap that you can actually see it easily in experiments. So this gap matters. But I don't like there to be a gap. I want it to go away. So how do I get rid of the gap? Well, I can simply use an Arno-Bohm flux to cancel the pi phase, or the -1 that came from the Barrier phase. So I take this wire, and since it's an insulator, I can pass a flux through the core. And all it does, if I can, all that the flux does is just to modify the boundary conditions. I can gauge the flux into the boundary conditions. So the only thing that happens is that as the particle now moves around, it picks up the flux that's going through the wire. And now you can see if I pass a flux which is half a flux quantum, phi 0 is a 1 flux quanta, h over e, then pi is cancelled by pi or minus pi, it doesn't matter. And I get periodic boundary conditions, and with periodic boundary conditions there's no gap. This is how it looks, and this is the calculations which you hopefully will do with Michael tomorrow. So, first of all, each of these parabolic bands is doubly degenerate. Why is it doubly degenerate? Well, because if it has a finite momentum in the transverse direction. So if there's one mode that goes like this, then because of time versus symmetry, the mode that goes like this has the same energy. So each of these guys is doubly degenerate. Once I add a flux, I break this degeneracy, and these two modes start to move apart. And then they rejoin again at half a flux quantum, where I effectively get time reversal symmetry again in the surface. But here, I now have this one mode, this linear mode, so there's no gap, and there's this linear mode which is not degenerate. And it's not degenerate because it has no momentum transverse to the wire, so it's just going straight. So the time reverse of that is its own time reverse. But now, something happened going from here to here. Because here I have a number of bands which are all doubly degenerate. Here I have a number of doubly degenerate band plus one which is not degenerate, which means that I have gone from an even number of modes to an odd number of modes. So we can just count. Here, for example, I have 2, 4, 6, 8 modes. Well, here I have 2, 4, 6, 7 modes. Does anyone remember why it may matter whether the number of modes is odd or even? No. It was yesterday. It was in yesterday's talk. Something. Yeah. Or it was actually the perfectly transmitted mode, which is, remember, if we have, which we do in both cases, if you have a Hamiltonian with is time reversal symmetric with a time reversal symmetry that squares to -1, then the scattering matrix is antisymmetric, which means that the reflection matrix is antisymmetric, which means that if I have an odd number of modes, the determinant of R is 0. If the determinant of R is 0, there is at least one eigenvalue of R which is 0, which means that there is at least one eigenvalue of the transmission matrix which is 1. That tells us that conductance in this case has to be at least E squared over 8, because each transmission eigenvalue gives conductance. If you remember the Landau formula, it tells us that the conductance is E squared over 8 times trace over T dagger T, which is the trace of T dagger T is equal to the sum of the eigenvalues of this matrix. And if one of them is 1, then this has to be larger or equal to 1. Okay? So what does that mean? Well, let's say I wanted to now see what are the different transport properties of a wire if I just vary the flux, and maybe I also vary the chemical potential. So let's just do something naive, which is just to count number of modes and hope that that's roughly what the transport is going to be. So I start now at phi equal to 0, and I'm going to vary the energy. As I vary the energy, I get 2 modes every time I cross a band. So the number of modes goes in steps of 2, but it's 0 at 0 energy, which is the Dirac point, the chemical potential here. Well, if I take half a flux quantum, I start with 1 mode, but I also move in steps of 2. But I start with 1, and the points where I go between are in between the points where I go in between on the other guys. Okay, so that's just counting the number of modes, but if you want to know what the real transport is, what the conductance actually is, then you have to do a calculation. And here's the calculation, or soon. So what I did was just to take Dirac fermion at this order, calculate the conductance. You can do it numerically. So I'm going to show you the conductance as a function of chemical potential. It doesn't matter what these symbols are, it's just the chemical potential of the energy that I just plotted when I counted the number of modes. And this is the conductance. It does roughly the same as the number of modes, except it has these tips which have to do with the density of states. This is for disorder strength delta, which is roughly the broadening of the levels with disorder. If I have an energy level that will broaden by disorder, smaller than the gap between the levels, so the level spacing. Now at half a flux quantum, at low energy I have conductance 1 because of the perfectly transmitted mode. See, it doesn't matter how much disorder I add. It will always be at least 1 because I cannot kill that mode. It's perfectly transmitted. Well, perfect means perfect. It's perfectly transmitted. And then if I go somewhere in between, I get something here. If I make the disorder very strong, then these oscillations will be washed out because you don't know that whether you have or not, how many modes you have if they all overlap. So these oscillations disappear if the disorder becomes strong enough. And something like this is kind of seen in experiments. I'm going to show you a couple of experiments. And what you should look for is that, so if I imagine that I fix my chemical potential here, let's say, I have only 3 curves, but I could, just from these 3 curves, I know how something like conductance as a function of flux is going to look like. So let's say I'm here. Okay, I'm shaking too much for you to know exactly what is here. Let's say here where the green curve has a peak. Let's see, that means that the conductance is maximum at 0, and then it goes to a minimum at half a flux quantum. and then it's periodic in this theory. While if I was here at some other chemical potential, it will be minimal at 0, and then it would go like this. Okay, so if I do conductance as a function of flux, I should see oscillations. This is an experiment that does exactly that, and you see oscillations. There's a big peak at 0, which has to do with presumably some weak localization effects. But the period is roughly corresponds to the flux quantum through the sample. So this is nice. Here are more experiments that do the same. Now this one is pretty interesting because what they do, well actually this one is pretty interesting because what they do is they can vary the chemical potential, and if you vary the chemical potential, you should see oscillation that goes from having a maximum at 0 to having a minimum at 0. And if you look at this with a loving eye, you can see precisely that happening. Okay. Some more experiments. I'm going to skip this one. That's the perfectly transmitted mode and some experiments. The problem with most of these experiments is that you can see these oscillations, and that's very nice. But if I wanted to convince you that through the transport data that I was seeing a topological, transport, I could not conclude that from the data. Basically, and the basic reason is that there are these wires are doped very far from the Dirac point, so there's a lot of modes. And if I want to see topological transport, I have to kind of go to the regime where I only have one mode. So let's try to get closer to that by going chiral. So what I want to do is now take this wire, and now it's not a cylinder but a square, because most of the wires in the experiments are square. And it's somewhat easier to explain what I'm just going to explain now. So now I'm going to apply a magnetic field, not along the wire, even if it kind of looks like that on the screen, but actually orthogonal to the wire. So the wire length is going like this, and I'm applying the magnetic field like this. Now if I make the magnetic field strong enough, then the top surface should go into a quantum Hall state. So it becomes an insulator. Well, if the top surface goes into quantum Hall state, the bottom surface goes into a quantum Hall state too. However, from the point of view of the Dirac fermion that lives on that surface, it looks like the magnetic field has the opposite sign. So if I'm a Dirac fermion walking here on the top surface, I see the field coming, through my head. While if I then go to the bottom half of the surface, the electric field is going in the opposite direction. Is that clear? What that means is that the quantum Hall state at the top and the bottom are a different quantum Hall state. It's like if the top state is plus nu, then the bottom state is minus nu. Now what happens at the interface between two different topologically distinct states? You have a net state, yeah. And in this case here, you get a net state at the interface between the two. That means on these side edges. So you have edge states even if there are no physical edges. Because the surface, from the perspective of the surface, it lives on a continuous manifold. You can calculate these edge states. So this is a spectrum of this system with a magnetic field. This is a momentum along the wire. And if you look at these states here, the ones that curve, if I look here at this energy, there's the edge state, and this orange one lives on this side and the blue one lives on the other side, and they move in the opposite direction. So in transport, this is what you would see. Now I'm putting the chemical potential at magnetic field at 2 Tesla, and I'm plotting for you the conductance as a function of chemical potential. And at 0 disorder strength, you just see the chiral modes up to the point where you hit the second band. So if you go back here, this is where you hit the second band. So that's in that particular case around 20 millieV. And if you add disorder, then for reasons which I'm not going to discuss, but it's quite interesting, close to the Dirac point, you actually break that chiral mode. Basically, you get scattering from disorder, but there is a large range of chemical potentials where you get perfect transmission. So this is for different disorder strength. This is very strong disorder. This is weak disorder. I can also plot at 10 millieV the conductance as a function of magnetic field, and you see that once the magnetic field becomes large enough, around half a Tesla, which is not particularly large, it's not a very strong magnetic field, I get this perfectly chiral mode. And again, disorder has to be very strong to kind of kill it. So that's the chiral mode. Now Majorana mode. So I think no one has talked about Majoranas yet. So, so I'm just going to give you a brief introduction to it. But maybe everyone knows what the Majorana mode is. Yes. Okay. Not everyone. So I'll spend a little bit of time on just showing you an example. It is the Kitaev chain, and then I'll explain to you how that is realized in these wires. So the Kitaev chain is a one-dimensional superconductor, spinless superconductor, and it's important that it's spinless. And this is the form it has. There's some chemical potential. There is hopping, this term, and then there is pairing. Now, in this case, the pairing is p wave because it has, if you Fourier transform this, then it has a momentum dependence. And you have to have p wave pairing if you have spinless fermions. But what happens now is that I can make a transformation of this Hamiltonian where I'm going to do the following. I'm going to take each of these fermions and I'm going to write them as a sum over two operators gamma b and gamma a, which have the property that they are their own conjugate, Hermitian conjugate. So they're kind of like their own antiparticles. So Majorana fermion is a fermion which is its own antiparticle. And they are fermions that satisfy these conditions. Now I can just put this in generally, but let's do it just for a couple of simple cases. First, mu smaller than 0 and t and delta is equal to 0. And then I get a Hamiltonian of this form. Now, pictorially, what this means now is that you see, actually, this should be J. I think there is a missing J here. So, but what matters here is what I did, I took a fermion on side I, and I wrote it as a sum of two Majorana fermions on the same side. And now this Hamiltonian is written in terms of these same fermions. So I made these two Majorana fermions, but I have to now make them again into a Dirac fermion, or a regular fermion, and I pair them on the same side. And then the ground state will look like this. If instead of taking this, I take this limit, I get this thing here. Now I have to pair Majoranas on different sides. So I have to pair the B Majorana on say J with the A Majorana on side J plus 1. So if I were to write this in terms of fermions, I can introduce new fermions, which are basically generated by combining these two Majoranas into fermion and these two into Majorana and so on. I see that the ground state is independent of this one and this one. The Hamiltonian is independent of this one and this one at the ends. So they are kind of unpaired. What that means is that I can introduce now a new fermion F here, which is the sum of this one and this one. It's a very non-local fermion, but this Hamiltonian is independent of this guy. So the ground state here is actually doubly degenerate, and the reason it's doubly degenerate is because the energetics don't care about this extra non-local fermion. So basically what happens is that I took one fermion and split it up into two halves, and these two halves are localized on the edges of the chain. So, and these are the Majorana modes that some people are hunting for vigorously. Is that clear? Give or take? Give or take. Okay. So how do we now get these guys in the wires? Well, this is the recipe. So, and what is nice about this recipe is that it's tunable. So I take the wire, which you remember is blue, and at this point I have no flux. And now I'm going to add superconducting pairing, and then the wire becomes red. It's a boring superconductor that is capped. And the reason it's boring is just that I have like these parabolic bands, nothing interesting happens. But if instead of having flux 0, I have flux pi, then I have this odd number of modes and a Majorana appears at the end. So you can roughly, it's easy to understand, if we ignore all the higher modes and we only look at this lowest mode, which is linearly dispersing, then that's essentially like the Kitaev chain, because it's a 1D, it's now a 1D mode, and you could write down, you can map this basically on the Kitaev chain. The magic of this model is that it doesn't matter. I don't have to do that. I can go higher up in chemical potential, but since I always have odd number of modes, I always get this guy here, this Majorana. So now I have a way of tunably, like turning on and off Majorana. Oh, that sounds kind of wrong. But turning on and off the topological superconductivity. So 0 flux, no Majorana, pi flux, Majorana. Okay, good. But now I want to find a way to see these guys in an experiment. I want to do transport, because I'm supposed to do transport. And there is a nice way to detect topological superconductivity via what is by some people called the Barrier Degeneracy, named after Benjamin Berry. And there is one paper here with first author, which is sitting in the back, Michael Wimmer. It's a very nice paper. So what they said is basically this. So I have now this superconductor, and I want to send in an electron. Now, as this electron bounces off the superconductor, it can either bounce back as an electron or as a hole. If it bounces back as a hole, that's what is called an Andreev reflection. Now, how can an electron bounce back as a hole? Well, in the superconductor, there's a condensate of Kuiper pairs, and I can always just add the Kuiper pair, which is 2 fermions, and then the fermion count is correct. So if this fermion goes in, and then I can take out a hole if I remove a. Okay? Yeah. So now, in this particular symmetry class that we are in, the Hamiltonian has this particle hole or charge conjugation symmetry. And the reflection matrix is unitary because there is no transport through here. And if you are in the single mode regime, these two conditions lead to this condition. You can do the calculation, but basically let's understand what this condition means. It tells us that the product of the reflection probability of an electron into an electron times the conjugate of the reflection probability of an electron into a hole is equal to 0. If a product of two things is 0, then either one of them has to be 0. And since r dagger r is equal to 1, they cannot both be 0. So it turns out that if the electron is reflected as an electron, that means that the conductance of this thing, the NS conductance, is 0, and you have a trivial superconductor. If it's reflected as a hole, then you have a conductance of 2e squared over h, because there's a Kuber pair that will be transported. Then this wire is topological. So now I just need to do this experiment. So, and I have two ways of doing it. Either I can make the perfectly transmitted mode here and make my chemical potential small enough that in the normal region here, which is the injector of electrons, I have the perfectly transmitted mode. Or I can apply a magnetic field here so that I get this chiral mode. And indeed, this is what you get. You get this is the NS conductance. It's 2 for the pi flux and 0 for the 0 flux. So I can tune here. I can turn on and off the topological superconductivity, and I directly see it in the conductance measurements. Now this range here, like I said, is hard to get to. It's hard to get close to the Dirac point, where the chemical potential is very small. The nice thing about the magnetic field is that if I have a 2 Tesla magnetic field, I can get a much larger range of chemical potential where I have perfectly quantized NS conductance at 2e squared over h. And again, here I'm just turning on and off the topological superconductivity by the flux. And when I'm in the chiral regime, then this part doesn't care about the flux. Now, there's a nice way to think about this as a Majorana interferometer. To do that, I have to do some maneuvering of my drawings. So this is a drawing. There's the chiral wire here, where there's a fermion that comes in, and at the interface with the superconductor, it gets split up. And the fact that it gets split up means that it gets split up into 2 Majoranas, one that goes this way and then one that goes this way. And then on the other side, it recombines and goes out, potentially. So I can redraw this as a source and drain, but now the source is the blue part here, where I have the incoming electron coming in here. At the interface with the superconductor, it splits up, and then it rejoins again. And the superconductor now is the drain. And you can compare this with, for example, this Majorana interferometer, suggested by these nice people here. The difference here is that the drain is kind of in the middle and the source is outside, but otherwise it's basically the same physics. But I can tune now this Majorana interferometer is basically tuned by the flux through this superconductor here. So that's pretty cool. There are other cool things you can do with these. I'm not going to talk to this in great detail. There are a couple of papers here. For example, for the chiral mode, if you have a PN junction, you can make what is called a Mach-Sender interferometer. But again, I'm not going to talk about this. And I think I'm actually basically going to stop here, because we are all tired and waiting for the poster session. So I'm a little bit early, but I think it's okay. So take questions, and thank you for your attention.
So at the very beginning, you started by saying that you were unhappy by the gapping of the cone, and then you wanted to get back.
Yeah.
But I'm thinking of one case where it actually might be good not to have the gap. which is this topological magnetoelectric effect.
But it might be good to have the gap, you mean?
To have the gap.
Yeah.
So instead of applying a magnetic field, you apply an electric field. And the prediction is that you should have a surface pole current. But if you have the Dirac cone, the surface and almost all conductivity coming from the bulk is exactly cancelled by the pi barrier effect of the Dirac cone. So in the end, the effect goes away.
Yeah.
But since here you very naturally gap the Dirac cone.
But don't you have to gap it in a way that breaks time reversal?
Yeah.
Because here you have time reversal, so I think it would, from time reversal between this one and this one, I think it would cancel also here.
One question? Okay, you and then Alex. Your motive is fine-tuned. You have to fine-tune the magnetic flux to get the Dirac state in nanohours. How sensitive it is to the deviation from the abstract function?
It's not very sensitive. And the reason is basically that, it's true that to have a zero gap, you need to fine-tune it to be pi flux. But then the size of the gap that you generate by being a little bit off depends on how far off you're from the, and that's not, it doesn't grow it doesn't immediately become very large. And then once a gap is much smaller than anything else, then effectively the transport is like you had an odd number of modes. Is that clear? Believable? Maybe. It doesn't. I mean, there is a. For example, if you calculate the range over which you have the topological superconductivity, it's a sizable range around the pi flux. I mean, it's. Oh, you mean without the magnetic field? Without the superconductivity? So you just mean the perfectly transmitted mode? Oh, I mean because of the way the disorder works and the perfectly transmitted mode, that also works pretty well. I mean that's basically because once you have a small gap, so a small gap and disorder with the Dirac fermion, they compete. And usually the disorder wins. So even if you gap it out, that doesn't mean that you localize, but rather you still flow kind of in the right direction.
Alex? Yeah, I wouldn't make sure I understand the nature of the perfectly conducting mode. So if you have a classic quarter wire, no matter whether it's topological system or not topological, typically generically localized, right?
Yes. Yes.
And then we have a conductance in relation to this conductance of E spread over.
Yeah.
But I wonder whether it's practical. I mean,
It's
perfectly conducting. I mean, how do you go from left to right to localizing right?
So no, that's right. So this is a matter of length scale. So if you're, I mean, strictly speaking, if I keep the circumference of the wire fixed, and then I take L to infinity, then yes, it will basically always be zero except for a very fine-tuned. But if I look at experimentally relevant values, for example, these few hundred nanometer circumference and micron long wire, let's say, then you're very, very far from the localizing regime. So you're much closer kind of to an effective two-dimensional. By the circumference, yes. I mean, it's certainly if I keep the circumference fixed and just keep increasing L, I will localize. I mean, that's. No, except for at that one point, yes.
You showed some nice experimental
There is, so for these topologically insulated nanowires, there is not much work with superconductivity. And the main reason, so if you wanted, let's say, if you wanted to, if I can qualify your question, if you wanted to go to the regime where you could see Majorana physics, then you need to reduce the number of modes such that the signatures of the Majorana mode is dominating your signal. But in most of the materials, somehow making these wires, it's somehow hard to control the growth such that that you can tune the chemical potential so that it's very close to the Dirac point. So there are not many experiments at the moment doing that, but I think there are people working on it. I think they will get there soon, hopefully. There are some experiments with superconductivity, but not probing this.
More questions? In the last part, when you have the two Majoranas, would there be a difference in the signature if you allow for hybridization between the two Majoranas?
Yeah, certainly if the wire is so short that they hybridize, now it becomes a matter of energy scales. So I need that energy scale to be smaller than whatever decay length. I need the decay length of that to be much smaller than the length of the wire. If it becomes, if it becomes larger than that, then I will lose the perfect signature.